Okay, we're back. We're live. It's Monday, and it's 1 o'clock, so that means we're here at SOAS, the School of Ocean and Earth Science and Technology, with a little sprinkle from IFA, of course. They're everywhere. This is, the SOAS show here on ThinkTech, and today we're going to talk about astrobiology and interdisciplinary science.
Yes.
Okay. With Jeff Taylor from the faculty at SOAS, Karen Meech from the faculty at IFA, the Institute for Astronomy on Woodlawn Drive, and Mike Mottl, who is also from the faculty at SOAS. And we always sandwich them. If there's a woman, we put them in between so it rotates. No, it doesn't mean anything. It's aesthetics, completely. So let's introduce you guys in terms of how you got where you are, what you're doing now, what is your role at SOAS or in one case at IFA. Let's start with you, Jeff.
Well, I've been working on planetary science for a very long time, but the planets had already formed, so it wasn't that long ago. And
he's older than he looks. Yeah.
And I study the geochemistry of the planets, what they're made of, how the elements cycle through them, how the crust of the planets are formed, and includes the moon too, and the whole the origin and evolution of the Earth-Moon system. And so I've been doing that for a long time, as I said, but here I've been here for 24 years in SOAS. And it is, I came here, everyone talks about Hawaii, beautiful place, but I came here because of SOAS. And
from where?
From the University of New Mexico. And I came here because it's what it does. It does so many things and does them well. And in addition, we also knew the Institute for Astronomy is quite renowned. And those of us who work on meteorites, that's just another way of looking at the stars.
Gee, I bet you've seen a lot in 24 years at SOAS. I mean, it's changed.
Oh, yeah.
So
It's
can you give us a
evolved and
dynamic
keeps
of
getting
how
better.
it's evolved?
Oh, when SOAS had just been started a year before I came, and it has changed so that we now have, I'm actually in a unit of SOAS called the Hawai'i Institute of Geophysics, which was there, but now we've added and planetology to it. So we have geophysics and planetology, the Earth and the planets. And that's a major change, but SOAS itself has, I think, has just blossomed. It's not because I came, maybe in spite of, but we can discuss that later. And it's a great place that has, I think, we have new ships since in those past 24 years. We have missions.
2 of them.
Yeah, and
2 submersibles.
2 submersibles. We have a serious involvement in planetary exploration missions, and what our goal is to actually be able to run one from here. In fact, Karen is the closest to be able to get to manage a mission from here. It would be built at JPL, but she can tell us more about that. But we have our foot in the door on those, and the oceanography is going so strong. It's Mike is the chair of the oceanography department, and all the operations inside SOAS, I think, are just going strong and doing creative work and bringing quite a bit of research money into the state.
So what is your official area of teaching or research?
It's a research job where, like all researchers at SOAS, we teach as well, both one-on-one teaching with graduate students, training postdoctoral fellows, but also some undergraduate teaching as well.
So what courses would you teach then?
In those 24 years, I've taught introductory geology quite a few times. I haven't recently because we've been focusing on other kinds of education programs. But I teach mostly graduate courses. The most recent one I taught is called, here's a good name, Petrologic Evolution of the Moon and Mars.
Wow. They
Sounds
come
very
far and wide for
scientific.
that?
Sounds very scientific.
Is this where the undergraduates come, or is that
No,
only
this
graduates?
is meant for graduate students. And last time I did it, I believe we had 10 students taking it. And it attracts people who are in geology, geophysics, but also we had a student from engineering and Institute for Astronomy, or astronomy graduate students. And so because you can do it in such a broad interdisciplinary way, like much of the work we do, it's makes it really an interesting class.
So where does SOAS fit, as far as you've seen it develop, in the scientific world of research around ocean and earth science? Is it right up at the front? Is it world famous?
Oh,
I can
think,
answer that.
Okay, there we go.
I'd love
Yes.
to answer that.
Yeah.
Yes, we had an interesting incident last year. Our dean was a visitor at University of Tokyo.
Also named Taylor.
That's correct.
You
Brian
can't have
Taylor.
enough of them. Yeah.
That's
No, you
right.
can't.
And he was evaluating the program at JAMSTEC, actually. And JAMSTEC had put together a little graphic that showed where they fit into the world of science in Earth and space
Great.
science. And they were very proud of the fact that they ranked number 20. And Brian Taylor came home with a copy of this graph because number 19, just ahead of JAMSTEC, was the University of Hawaii. And most of the top institutions were government agencies. And if you just looked at the universities, we ranked number 9 in the world. And the measure here was scientific productivity in terms of papers published in Earth and planetary sciences. And we were number 9 in the world among universities.
Let me drill down on that for a moment. So what does it take to write a paper? Do undergraduates write papers or only graduate students write papers? Do professors write papers?
Professors, one of our major jobs is to write papers.
Okay.
The university does teaching, but it produces scholarship. And in science, that means publishing scientific papers. There's a well-established set of journals that we try to get our papers published in.
Name some.
Science and Nature are probably the two most prestigious. They're sort of general science journals, but we all have our favorites in our own discipline. I'm a geologist like Jeff. My specialty is geochemistry. The top journal in geochemistry worldwide is called Geochimica et Cosmochimica Acta. And that is the place to publish if you are a geochemist. If you can't get it in there, then there are other journals of somewhat lesser stature. But one way or another, it's very important that you get your work published. We have an expectation in SOAS that we publish 2 to 3 papers a year, actually.
How hard is it to write a paper?
In science,
Sorry I asked that. I mean, it's a painful question.
the vast majority of papers start with an idea and with data collection, because that's what we do in science. We collect evidence.
So it may be off your own work as a researcher.
Absolutely.
In fact, it likely is off
In
your own
all-
work as a researcher.
Almost all
It's what
cases.
you do. Okay.
That's correct. So you do the research, you have an idea, you go out and collect data in the real world. We do a lot of field work. You formulate the data, you analyze the data, you interpret it, try to figure out what it means, and when you think you've solved all that, you've reviewed the relevant literature, then you're ready to sit down and write a paper. And I think the first time you ever do it, it takes many, many months, sometimes years. But after you've been doing it for a while, as Jeff and I have, I've been at SOAS for 28 years.
That's longer than 24, Jeff.
Yeah.
I know. I was waiting if he was seasoned enough to be.
I can't let him get away with that.
Give him a break.
Exactly.
And another important thing about writing papers is that we can write a paper once you have the data fairly fast now. But we work with graduate students to teach them how to do it. And that
Sure.
it's a kind of labor intensive, and it's hard for them at first. It's harder
But what
for
do you
some
teach
than
them?
others.
Do you teach them how to write scientific language? I mean, I've heard it said at this table by people from SOAS that you begin with the charts and graphs, and you spring out of the data, and you show the charts and graphs, and you make your conclusion, write it up in text, and that is the seminal aspect. Is this right?
A picture is worth 1,000 words,
Yeah.
and the
Yeah.
way we present our data is in graphic format. And this is exactly what I teach my students. Do the tables and the figures first. Understand what they mean. Each figure has a point, and the paper then consists of enumerating the points that are already made in the figures.
So the better your charts and graphs, the better your paper.
And of course, that is all sitting on the underlying data. You have to have high quality data to make the graphs in the first place. That's the evidence.
And try to get them to write it in actual English.
What do you mean by
Rather
that?
than-
I mean, I
rather than it has to be technical enough so you're not afraid to use certain jargon for a specialized journal, but you really do want, especially for what we do is a lot of work that involves other disciplines. And so you have to be able to communicate with them across those disciplines. And that means you have to write clearly it's a bunch of scientists. I mean, we don't have to write clearly so that someone in the English department who doesn't have a technical background would fully understand it. But you know, even for that, they ought to be able to get the gist of that paper.
And sometimes it's harder for the full-fledged faculty to do this because the faculty is so immersed in their specialty that they are out of practice for explaining it to the non-specialists. So sometimes the students do a little bit better job.
Sorry about the interruption. Well, you know, in law, okay, lawyers tend to write very, convoluted, arcane statements, and sometimes I think it's to confuse people. Maybe a lot of people must feel that way. But you know, the effort of the Bar Association to try to teach you how to write plain English. In fact, there are statutes back in Hawaii, back 30 years ago, that encouraged lawyers to write plain English. I don't think they've worked very well, but there you have it. You know, the attempt to make professional writing into writing that can be read by anyone. And I mean, I put this to you, Jeff. I mean, if I'm a student, say a high school student or a young college student, thinking about geology and the like, am I going to be able to read these papers, or are they going to be loaded with acronyms I don't understand?
Well, I think geology majors ought to be able to read any published scientific work. And if they aren't, either the fault lies with them not learning enough in school, or the article is simply not written at the right level.
So you're gonna teach your students how to do this. You're gonna
Yes,
teach
it's
them
a
how it
very
looks in the
important
other
part.
way.
You know, a PhD student has to write. Typically, we require 3 full-length papers for a dissertation, and they have to write that and write it clearly and have it be publishable.
Mhm.
And it's a very important skill.
Do you grade them on the papers? Yeah,
If they're part of a course, yeah.
part
on
of a
the-
course. So if I take a course in, say, in geology, part of the work in that course is a paper, right? I do research, I write a
Yes,
paper. It's a
yeah,
graduate-
and for graduate courses, almost always, and for undergraduate courses, UH, we do a big effort on writing intensive courses so that there is a requirement so that a student, you know, I bet you they can go in some semesters, a student might have 5 courses that are all writing intensive so that they learn to communicate. And I think that emphasis started in those about when we came. Maybe it was going before, but they have really pushed it for the undergraduate education. And I think it's very, very important.
Well, so can a graduate student writing about his research or her research get into these professional journals, these science journals? Or is that
Yeah.
reserved for professors?
No, in fact,
Oh,
as
no,
Jeff was saying,
no.
it really is required. The 3 papers that is a thesis in the geology department, for example, those are generally published with the student as the first author.
In these major scientific publications?
Yes, and
In
of course,
fact,
the
they're
more
reviewed.
the more important the piece of work, the better journal they're able to get it into typically. But that is our goal. We want our students to be publishing in the top journals. That's part of their
Give them
education.
a good grade if they get in?
At that point, the grades aren't so important anymore.
Yeah. You know, we also have programs at the UH for undergraduates. One of them I'm very familiar with is the Hawaii Space Grant Consortium, and we have a fellowship program. The students in it, there's 15 on average full fellows who do a research project with a professor who mentors them along. And at the end of that, at the end of a year, or 1 semester if that's all they had required, they have to write a final report. It's a 5-page paper that we put online. We used to distribute them. Remember those things with the paper stuff? Distribute them at the libraries. But now we put them online. But they're full-fledged, and they have to be quite thorough, have the data in it, and charts and graphs. And so
Somehow there's a comfort in knowing that science moves the same way business moves. That, you know, years ago it was about paper.
Yeah.
Now it's not about paper. You know, Karen, I want to come to you, but I got to take a break first. After that, you're going to have the whole channel. Okay, we're going to find out everything from you.
Okay.
This is Karen Meech. She's from IFA as opposed to SOEST. Today we're doing the SOEST hour. We're talking about astrobiology. We haven't gotten to that yet. And in interdisciplinary science, which is certainly relevant to that. I'm Jay Fidell. This is ThinkTech. We'll be right back.
Hello, I'm Martin Despang, and I'm the host together with the one and only Ali Yamashita, and our show is called Urban Transcendence. And urban transcendence is about identifying where we have a unique situation of a vibrant city in one of the most beautiful natural environments. So how these two can coincide, sometimes conflict, how they could find reciprocity in the 21st century is what we're excited about. And we're planning on bringing in a diverse body of guests, both from the arts and the science and the established and the wise and the emerging generation. So hope you will join us. We'll always be on Thursdays from 1 to 2 p.m. Thank you.
Okay, we're back. We're live. We're ThinkTech. We're talking about SOEST, the SOEST show, the School of Ocean and Earth Science, and IFA, the Institute for Astronomy today, special. We have Jeff Taylor from SOEST. We have Mike Mottl from SOEST, and we have Karen Meech from IFA, which is one of my favorite pieces of architecture actually in the university. It's not on campus, it's on Woodlawn Drive, and there are shops and restaurants nearby, so there's a lot of benefit to being in IFA. So tell us about life in IFA.
Well, I'm a research astronomer, and I got my first job at IFA actually straight from graduate school. I came out to Hawaii, not because of the beautiful climate, but because of the beautiful facilities on Mauna Kea. It's one of the best places in the world to do astronomy with the telescopes there.
How did you get into astronomy?
Well, that's an interesting story. I liked science as a kid, and Star Trek came on in the 1960s, and I said, that's what I want to do. I've got to study space.
You're giving away too much information.
And then I decided that the most exciting part of astronomy was actually planetary physics, and so I specialized in comets and the relationship to understanding how our solar system was put together. And that's evolved into this field of astrobiology, which is more looking at the origin of life and life's ingredients and how the solar system is put together.
Did you go to see Alec Filipenko just a month ago?
No, I was out of town.
Yeah,
No, he's an
that was quite a
excellent speaker.
speech. My favorite part of that speech, you know, I'll tell you people, my favorite part of that speech, which was astounding, was when he did Q&A, and these kids came up, and they were anywhere from 6 years old to 15 years old. And and they gave him questions in astronomical physics, and they were brilliant questions. I didn't understand the questions, and he would say things like, "Okay, we're going to write a paper together," but I get top billing. What a guy! He's out of was it Berkeley?
Berkeley.
Yeah, and he got the Best Professor of the Year award in Berkeley for the past 9 years, or something to that effect. Anyway, it's a very interesting area, but it strikes me that here we have the Institute for Planetary Geophysics.
Something like that, who knows?
Planetary, what is it?
Hawaii Institute of Geophysics and Planetology.
Geophysics and Planetology, and that's your kissing cousin down the block in SOEST, right?
Mm-hmm.
So do you get to talk to them?
Absolutely, and one way we've been doing that is we've become part of the NASA Astrobiology Institute, which is a large interdisciplinary institute that's distributed in the U.S. And the sole purpose was for NASA to better define some of the underlying science for their missions. And it's required to be interdisciplinary, which means you're looking at very big picture questions that require numerous disciplines to come in to be able to answer things such as where did water come from on Earth? Big fundamental childlike questions that we still don't know the answer to.
Strikes me though is when you have all these interdisciplinary issues that ultimately there will, it's because there's no specific science to cover that. So you bring in all your experts from other sciences and they take a whack at it. But one day, there may be somebody who does that science specifically.
Not necessarily. For example, the question that we're focusing on that leads to where did water come from on Earth really requires astronomers, geologists, geochemists, cosmochemists. No one person has all the answers, and in fact, you don't even know the questions to ask until you're exposed to a completely different way of thinking. So I think this is going to be the way of the future, is to really train people to think in big picture questions as opposed to very minute details of a sub-discipline.
Yeah, so maybe it's just the other way than what I said. It's that what happens is you get all the interdisciplinary people studying more subjects, not fewer.
And and whole new perspectives on them because you're looking at it through someone else's eyes, and it works great.
And this helps you with your appreciation of it,
Yes.
with your vision of multiple
I think
disciplines.
that's
Yeah.
where innovation will come from.
Yeah.
And I think my favorite examples are the kindergartners. They are not afraid to ask questions that we think of as obvious. And so there's where some of the really key science is going to come from.
Those are the kids who asked Alex Filipenko those tough questions.
Yeah?
Yeah. Yeah.
So what is astrobiology? Let's get to our title question.
It is the study of the origin of life, how the ingredients for life were made in space, how you create habitable worlds, and what defines habitability, and are there places in our solar system and elsewhere where life may exist currently.
That's pretty sexy,
Yeah,
because that leads to the possibility of other equivalent life out there somewhere. Man's great quest to find somebody like man, or
Yeah.
woman.
although we think probably the first life that will be discovered will be microbial.
little wee things.
Yeah.
So what was Dave Carl doing before he got involved in SCOPE and Seymour?
Of course, Dave is a microbiologist and
Yes.
has been doing that for many, many years. Trained as such as a graduate student, looking at microbial processes in the ocean. Microbes have been here longer than anything else on the planet by far, and they set the stage for all the other higher forms of life in terms of, for example, producing oxygen in the atmosphere in the oceans. So what Dave was able to do with Seymour, with the Center for Microbial Oceanography Research and Education, was to put that all together, because by that time the field had matured. There was tremendous interest in it scientifically at the National Science Foundation and among foundations, and Dave was able to put together then that really world-class institution that he talked about last week on our show.
We took some film of Dave giving us a tour around Seymour last Friday, and first thing, me and the camera crew, we all reported directly to SOEST. Wasn't that SOEST? Excuse me. I'm going to throw it in a pot of water.
It is certainly part of SOEST, however.
Yes.
It's physically located down the block.
Yes, well, yeah, up the street. And it's very interesting. Beautiful building.
Yes.
Beautiful building. I mean, when they talk about how UH needs $500 million worth of, maintenance and repair, not at Seymour.
No, not there, no.
Not at Seymour. Anyway, so he's been studying microbial things, animals, or whatever you call microbials, in the ocean, and I guess you've been studying them in space. What's the comparison? What's the difference?
Well, we're not studying them in space yet, but what people are doing is trying to figure out what would be the fingerprint of life in space.
You haven't actually found it.
No.
Oh, that makes it even more interesting.
One fingerprint might be, are the gases in a planetary atmosphere a little bit different from what you'd expect from pure chemistry, because microorganisms make a lot of chemicals that you wouldn't expect to coexist. So those are the sorts of things that astrobiology tries to address.
Wow. So out there somewhere, maybe in our lifetimes, we're going to find it.
Oh, I think so. I hope so.
What's your sense of the track of it? I mean, are we close?
We've discovered a lot of places in the solar system that are potentially inhabitable by microbes.
An environment of compounds, I guess.
Life needs water, it needs energy, it needs organic compounds and the elements for food. And we've seen a lot of places in the solar system that meet those requirements. Subsurface Mars, there's water. On Europa, one of Jupiter's moons, there's a subsurface ocean that people speculate could have life in it. One of the moons of Saturn has shown to have huge geysers of material erupting from an ocean. And when they looked at the chemicals in the water, it has some of the ingredients needed for life. And so it's an exciting time to live in, because we might be able to discover microbes in our solar system.
Well, if you do, then you're going to discover the similarities or contrasts between the way it works on Jupiter and the way it works on Earth. And that will give us a much deeper view into exactly how life is created. Oh, wow. I mean, it makes me feel religious. Not really, but.
Well, we're first trying to get at the ingredients for life. You know, we're actually planning to try and develop a space mission from UH to look at some of the ingredients for life, namely water. How did Earth get its water component? Because we don't actually know that for sure.
So, at this point, a space mission from IFA, from SOES, from UH, would be to discover the elements of the environment and to see what's out there that might be sufficient to allow for the creation of life.
Well, we're particularly focusing on water. There's some objects in the asteroid belt that seem to have water ice, and we think it might be chemically distinct from what we have elsewhere in the solar system. So we want to look at that to see if it was something that could have been delivered to Earth early on.
Delivered.
We think Earth
This
may
is
have...
sounding more and more like Star Trek.
Well, Earth may have formed in a region so close to the sun where it was too hot to originally get a lot of water. So that's one of the big questions. Are we unique in that we have water on Earth? Did it require some special circumstance to get it here, or is this a common process elsewhere? And there's a lot of extrasolar planetary systems that...
Let me make I don't mind making completely naive guesses. With you guys, I can do that. Make me a undergraduate.
Okay, okay.
But if I have hydrogen, and I have oxygen, and I have energy, why can't I have water anywhere those three things exist? Only thing is they won't have microbial things inside the water. I mean, or that may be different from place to place. But can I make, pure water anywhere those three things exist?
Certainly had water all over the place in the solar system, but when it was close to the sun and hot, it was in the gas form. And Earth is too small to capture gases. And the only way it can capture things easily is if it's in rock form or ice form. And Earth was just too hot. So one idea is maybe comets and things that were formed farther from the sun where it was cold. They slammed into the Earth early on and brought some of the water.
But it sounds from that like you had to seed Earth with water, that some water would come from somewhere else, and once here, it would somehow provoke the creation of more water. I mean, is that part of what you're saying?
No, we may have got captured a little bit in the gas. We may have had to have comets and asteroids hit the Earth and deliver it. And some people think that when the Earth had a molten surface at one point, it could have manufactured water by the minerals in the magma combining with hydrogen in the solar nebula.
Yeah, you still need oxygen and hydrogen. I mean, but there's really plenty of both.
Yeah.
And
Can we find them on Jupiter?
It's predominantly hydrogen.
predominantly hydrogen. Yeah. Yeah.
Surfing.
Yeah, the organic compounds are important too, because they can't come in. The Earth was very hot early on, especially if the moon formed by a big impact. It become extremely hot environment, and the organics probably got all cracked, and so that may have to come in late. And one of the things we're working on in this collective in our astrobiology program is to look at two case studies of organic water interactions. One led to life and one didn't. We have these meteorites that are rich in carbon, carbonaceous material, and including amino acids. Just that there's way more amino acids in them than the ones we use for life on Earth. So this was entirely done without biology, and we're trying to understand through looking at the meteorites and understanding the organic chemistry and the interaction with water and heat, why that didn't go to life and what did it go to, because maybe that's the nature of the material that did go to Earth that did seed us. And then the other place is active environment on the ocean floor to study the organic water interaction and rock interactions there, where there is already life, but maybe life starts again. And what's going on at the ocean floor, and Mike understands that part much better than I do, but we send instruments down to the seafloor to study it, and we study meteorites in the lab with fancy instruments to understand that. So
Yeah, this might be a good place to show the graphic of the facilities, all the facilities that we're bringing to bear to look at some of these questions. is
See if we can find a graphic here.
we have the telescopes on Mauna Kea and
Mhm.
Haleakala. We've got the deep subsea floor in the upper right-hand picture shows instrument sled down at the seafloor sampling some of the fluids. We've got some of the laboratory, both studying meteorites and the chemistry in space. We actually have another better picture of the laboratory that studies the meteorites with the picture called Katie.
Yeah, do Katie. There's Katie. She's one of our graduate students who, in her case, she's studying the water content in lunar samples, which we used to think was completely free of water, but they are not. And to understand it and to compare the hydrogen, it has a heavy isotope called deuterium. That ratio changes with processes, and we're trying to understand it. Notice how happy our students are.
Yeah, well, can
The-
we dwell on that laboratory picture for a
Yeah.
minute?
Yeah, it's worth noting that's a single instrument that
That
you're
is
looking
everything
at.
you see
It
there
fills an entire
is
room.
a-
What is it? What does
It's
it tell
called
us?
the secondary ion mass spectrometer, or SIMS. That sounds sciencey.
It's
Doesn't that
appropriate
sound
to have an
sciencey?
acronym for that.
Yeah, you got to. And it is, it sputters, it shoots a beam of ions. She uses cesium in her study that sputters holes in the rock that are only a few microns across, and we can show you a sputter thing. Do the Robinson, see those two holes, square
Yes.
holes?
Yes.
That's done by this ion beam, and it's on top of a mineral called apatite, which is a phosphate mineral. Kind of
you say
important to life.
apatite?
Apatite, yeah. It's
Apatite.
actually important in, phosphate's important in fertilizer.
That's what your
Should
teeth
point
are
out
made
the
of.
scale.
That's what your teeth are made of. And the scale, see the scale is 10 micrometers down at the bottom.
Okay.
And
It's tiny, tiny.
the central pits, the deepest, darkest ones there are about 10 microns across. So what this does is we can analyze at those tiny spots
What?
the hydrogen, the total hydrogen content, and its ratio to this heavier hydrogen called deuterium.
Material.
And all in situ, and with that instrument that is in the basement. What's really interesting, that's nanomicron scale anyway, and we study but we have other gizmos that study it at the nanometer scale. So we study the cosmos from nanometers to light years when you use the telescopes.
This
It's
is
really
man-made.
cool.
This tiny little thing.
Those pits.
The pits the rock is natural. This is a lunar sample with this phosphate mineral in it, now decorated in our laboratory with these pits.
So if I'm in another discipline, if I'm in, I don't know, chemistry, physics, astronomy, I need to know about this.
Yeah, this instrument sits in the basement of the post building because it needs stability. Any tiny vibration, it won't work. So it's in the basement on a very thick slab of concrete. When we first got it at UH several years ago, it was only the second one in North America. Cost $3.5 million, most of which came from the National Science Foundation. Some came from the state of
And
Hawaii.
NASA and the Keck Foundation.
Yes. So
The
it,
same guys with the telescope.
Yes.
there are only a handful of these even today in all of North America. So this is a very important and highly specialized instrument that's capable of making measurements that you just can't make any other way.
Who supervises this?
We have a staff. It's run by another professor, Gary Huss, his name is, who's an expert on this. And he has the lab manager is a genius on these things, and even designed an attachment for this thing that the images the ions at a resolution of way less than a micrometer. I mean, the guy is amazing. His name is Kazu Nagashima. And then we have an assistant lab manager as well now.
It's part of SOAS.
Part of SOAS, yes.
You were going to say?
Well, one reason that you need to know about this, even if you're an astronomer, is it provides some evidence that we can use related to astronomy. What is the fingerprint of water coming to Earth or Mars or the Moon? And this is the tool that will get you those fingerprints in the actual samples.
Common denominator. You can use this to confirm your conclusions in the astronomical scenario.
Yeah, you can get astronomical fingerprints, but this is one way to connect it to the solid worlds.
That's pretty exciting. You guys have coffee regular?
Yeah.
Yeah, we purposely, and you mentioned you have to, physicists should know it, and chemists should know it, but in a way, to operate that SIMS and to understand what you're studying, you actually have to know physics and chemistry and or at least work with a lot of people who do in order to make the measurements, to interpret the data. And what's another amazing thing that has come out in meteorite studies is that there is, inside meteorites, not all, but many, leftover dust grains that pre-existed the solar system. So they're interstellar dust particles preserved in meteorites. We identify them by their quite different isotopic composition.
You can tell that they're older than.
You can tell that they are very different in terms of their isotopic composition of elements that don't vary anywhere else in the solar system except in these. And the objects, the big ones are only 10 nanometers, that's 10 billionth of a meter. That's what we geologists call wee. And
WEEEE to the 27th power.
And anyway, so those are the stardust. And then we use big telescopes to study interstellar space, study stars, study the stars that have blown up to seed interstellar space. So it's all wrapping around together, and you study these little objects. You're doing astronomy, but in a lab on materials, and it all ties together.
I'm
And that's
beginning
what
to
we're
see
trying.
the Captain Kirk thing now. You know, Filipenko talked about how old the universe was, and I forget how old, but this is your what do you call it? Your dust
Yeah.
would be older than that.
13.7 billion
That's right. That's
for the
what it said.
universe.
Yeah.
Our solar system is about 4.567 billion years old. So our solar system is about 1/3 of the age of the universe itself.
And this leads to all kinds of thoughts about what happened. How did this all, what's the timeline? How did this happen? What forces drove it?
And we have made amazing progress in the last 10 or 20 years in working out that timeline, in part using instruments like the SIMS.
So the instruments have gotten more sophisticated, more expensive. You need more training to use and make sense out of them. And SOAS has kept up with that.
Yes.
Yes, we are one of the leading such institutes. In fact, one could argue SOAS is potentially the largest Earth and Space Science Institute in the United States, certainly at any university. We also pretty well run the gamut in terms of the total sum of disciplines that make that up. So yes, we are one of the top Earth space organizations in the United States.
We want that.
And of course, our alliance with the Institute for Astronomy, in part through the vehicle of the Astrobiology Institute, really makes us unique and gives us a strength in this wide range of disciplines that you really won't find anywhere else. And one result of that is we're able to attract to Hawaii absolutely top talent in these fields of science.
It's not just a linkage to astronomy, it's chemistry, information and computer sciences, so we have at least 8 departments that are connected together by virtue of having the interdisciplinary science.
Anything outside of SOAS and IFA is in this collaboration? What, chemistry, is that a separate department?
Yes,
Yeah,
chemistry in a
chemistry.
different college even. Chemistry,
And information computer science is
Oh, of
in a
course,
separate department, separate school.
So you're all sort of working in this team where you share and you collaborate, you find new thoughts, new subjects.
and really that's the whole idea of the Astrobiology Institute, is we have gained truly novel insights into how things work by virtue of having these people from all these different disciplines looking at
And
us.
that's great.
Yeah,
In fact,
Karen,
that CAN 7 graphic kind of
Yeah, have a
shows
look
some
at-
of our connections.
let's have a look at that one. This would be a good time.
Oh,
So,
okay.
yeah, we've
I like this one a
I just
lot.
like looking at it.
very cleverly designed all the circles to be water molecules, H2O. And then we've tried to tie together the different disciplines from astronomy to
That's
the
cute.
geology, geochemistry, biology, to focus on the fact that we're all collaborating to answer some really big picture questions.
Is that Aloha Tower I see in this?
No, that's the deep subsea floor
Okay.
sampling system.
So what are your challenges? I mean, this is all really at the cutting edge, seems to me. Of thinking, of human thought, actually. But what are your challenges? What holds you back? What would you like? What barriers would you like to overcome to get to the next step?
Some of it is actually both technology and really big instruments. You know, as great as Hawaii is with premier astronomy and laboratory facilities, we need bigger telescopes and we need to get into space. You know, getting samples back from these
That's
places.
why the trip is so important. Yeah. So what would be the UH role in the trip? I mean, that's
You
pretty
mean like
major
the mission?
mission. Sorry. Yeah.
We would be the lead. We would partner with space industry to build the spacecraft and the instruments, but we would lead the mission, we would lead the science, and the data center would be here at the University of Hawaii, where the data comes straight from the spacecraft to us for the analysis. And these are half
Karen is
billion.
being too modest. She is the principal investigator in the proposal that's been put forward to NASA, so she would lead the mission to a main belt comet.
That's
has
terrific.
Been proposed.
She's a
terrific.
driving imaginative force behind it too.
But now, does the Gravity movie have anything to do with this?
No.
Okay.
No,
Fortunately.
I believe Mike and I disagree on that. I think that movie was great.
No, I like the movie. I just wouldn't want to experience it.
Oh, I don't want to experience it. No, no, no.
So when do you think this thing could get off the ground? I mean, off the lift pad, so to speak.
Well, it would have to get approved first. It's still in the proposal stage, but we would launch in about 2021 to
That's
get
not
there
far.
in 2027
And where would it go?
to the outer asteroid belt to explore,
Of the universe.
no, of
No,
our
just
solar
our
system.
solar system.
Okay.
And believe it or not, it's actually hard to get there. It's going to take 6 years of travel to get out there.
Okay. How do you know you're there when you're there?
We will gradually approach our object. It will get bigger and bigger, and then we're going to spend 6 months at the object sampling, not sampling directly, but looking at the gases.
Am I right to say this is further than we've ever gone before?
No. We've actually had many, so this is a small class of missions. We've had many missions that have gone to the outer solar system. And in fact, there's one en route to the farthest former planet, Pluto, and it will get there in 2015, I believe.
And the old Voyager went out of the solar system finally.
Yeah, the asteroid belt lies between Mars and Jupiter and is generally considered to be what should have been an additional planet that never was able to form because of the gravitational disturbance caused by the proximity of Jupiter. So the asteroid belt are these bunch of rocks floating out in space between Mars and Jupiter.
We're almost out of time, and I do want to handle this really, to me, an important question. That is, the public, which may get to see this. Why should they care about your work? Why should they care about your work in geology? Why should they care about your work in these instruments? Why should they care about your work in this mission? What does this mean to the fellow on the street or woman?
Well, I think it's answering very fundamental questions of where did we come from? How did we get a world with life on it? To me, I think that's one place we would care.
I think all humans are interested in knowing what's out there. Are we all alone, or is there other life out there? And obviously, is there other intelligent life out there? That's really what the Astrobiology Institute from NASA is all about, is addressing those questions. And the best way we know about to try to answer that is to determine the range of conditions that are required for life to form, and whether those are extremely rare or whether they're in fact relatively commonplace. So that's really what we're focusing on with our Astrobiology Institute, to answer questions: is there life out there outside of Earth, and where can we best look for it?
It also gives you a whole new perspective on the world around you. Anytime you learn something new, I mean, it's a great experience. And here's a local example I've done. There's a field trip we all take who teach geology around southeastern Oahu. You go, it's Diamond Head, Hanauma Bay area, and Makapu Point. And anyway, at the end of that trip, we used to do a lot of teacher training for in-service teachers, already have jobs, and take them on this trip. And so many of them who grew up here and have been to the beach, driven around southeast Oahu, said that, wow, we'll just never look at those places the same again. And I think that's the same, in a bigger way, the same perspective you get when you get hints about where life could be, how it could form, how the planets, where they come from. I mean, how did it form? What's the relationship among its parts and pieces, and how does it relate to us? So I think that's a fundamental thing, without getting into the fact that actually it's a lot of grant money comes in.
Well, I wanted to ask you about that. I guess that'd be my penultimate question. I mean, from the writing you talk about and the research you talk about, it sounds like this would be pretty attractive to a lot of funding organizations. How are you doing in funding?
Our research group has brought in about $12.1 million so far, and we've just put in a new proposal to renew. But the beauty is that has leveraged at least 2 times as much money to come in from other sources to help with the research enterprise, both for instruments, education, graduate training, and public outreach. And so I think it's a very attractive field for grant money.
Yeah. And does a 30-meter telescope mean a lot to you?
Oh, it'll be exquisite because it will make measurements that we can't now. You know, I know extragalactic people are excited for the rest of the universe, but it will do things close to home that we can only dream of right now.
I think I saw some of those on Star Trek, the extragalactic people.
This will be the best telescope in the world in the best site in
Yeah,
the world,
yeah, we
namely
need
the
it.
summit of Mauna Kea. Very important for Hawaii that the 30-meter telescope will be here.
So the more writing you do, the more publishing you do, the more imagination you display in figuring out your hypotheses, the more likely you'll get funding, the more funding you'll
Absolutely.
get.
Yes.
Yeah.
Yeah. And it leads to so many other things. We have a little research project, this leads to bigger ones. We just put in, speaking of missions, a proposal that one of my colleagues named Paul Lucy is the principal investigator of, to send an instrument to Mars in 2020. It's going to be a mission to Mars to study it the way Curiosity is doing it, but with new instruments being chosen. He's the principal investigator with an instrument developed here, which would zap rocks, but also measure their mineral content and search specifically for biological or compounds.
Boy, that'll be interesting.
And so if we get we should know in a month or so about that one, and there was quite a lot of competition, and so we put in this big team effort, but a lot of it is done. A key player in this was a graduate student who was funded by our astrobiology program, and to do laboratory measurements of some of both the biological part, but also the elemental and mineralogical part, and we all wouldn't have known each other if it hadn't been for all of us working together.
But it's important too, this provides opportunities for the next generation of scientists, for students and to train students.
They coming in?
Yeah.
Are they knocking on your door? Are they also interested in the origins of the universe and of life?
Absolutely.
Yes.
It's
Yeah.
a draw for Hawaii.
Yeah.
So my final question, which I've been holding back for the end, because you guys, you know, as a professional matter, probably by this time it's a personal matter, you must have hypotheses in your own mind, not proven, just imagination about life in the world. And I'd like you to tell me, in your secret thoughts, how you think it's what you think you're going to find.
But it's tough. I mean, I think life is absolutely out there. I think it's most likely we'll find the microbes in our lifetime, but there are programs that are searching for technology of life. That's a little less certain, but I think it's absolutely out there.
Aren't you afraid it'll eat your finger?
No.
It'll be friendly.
They can't be worse than we are.
We got our studio staff laughing over here. What about it, Mike? What do you think?
I still think there's about a 50-50 chance we'll find microbial life in the subsurface on Mars. This is, of course, our nearest target that we've been looking at closely for quite a number of years now, and life has been a focus for all of that research. There isn't going to be any on the surface at the present time. It's just too harsh. But we have learned enough now about the subsurface of Mars that there probably is liquid water down there. And it's not unlikely that life might have begun on Mars in an independent initiation of life 4 billion years ago, give or take, and that life might still be harbored in some deep recesses where there's liquid water and planetary warmth in the subsurface of Mars.
But you forget, we could in fact be Martians.
That's another, not
So
impossible.
like the Polynesians came from Polynesia,
Yeah.
people came from who knows where. Yeah.
Yeah, Jeff can certainly tell us from our meteorite collection, we have 20 to 30 meteorites that we are quite certain
We're up to
came
60
from the
now.
surface of Mars. So there is an exchange of rocks among the inner planets in the solar system. So had there been life originating on Mars, perhaps earlier than Earth, Mars might well have seeded Earth with life. This is an old hypothesis, by the way, called panspermia. Goes back more than a century, and it's now alive and well again.
That's great. Sometimes earlier thoughts are validated.
Yeah.
So we don't have any more time. We're done. But that's Jeff Taylor over here, Karen Meech in the middle from IFA, and Mike Mottl also from SOEST. We've been talking about astrobiology, in case you hadn't noticed, and interdisciplinary science, and it's been great. And it's only the beginning. I want to do this again. You know, this is fantastic, fantastic. I want to go to school again. You guys are very provocative. Thanks very much.
Thank you.
Thank you.
Our pleasure.
Aloha.